Today we will discuss the partitioning effect in organic reactions and its impact on primary kinetic isotope effect. As you all know, primary kinetic isotope effect is seen when the hydrogen is replaced by deuterium, and if the carbon hydrogen bond breaking takes place in the redetermining step, then we observe a decrease in the overall reaction rate of the reaction, since the carbon hydrogen bond breaking is taking place in the redetermining step. And we all know that the pKi effect is observed by observing the value Kh by Kd ratio, which is almost equals to 7, more or less 7. But sometimes the Kh by Kd ratio in certain reactions was found to be between 1 to 3. And in those reactions, the redetermining step does not involve any CH bond breaking. So what is the cause for this slight increase in the Kh by Kd ratio? To understand the phenomena, we have to consider an example, and then we will discuss about the partitioning effect. Okay, so let's consider the simple aromatic substitution reactions. As you know, for all the electrophilic aromatic substitution reactions, the redetermining step is the first step, except for the sulfonation and iodination, in which the second step is the redetermining step. So the majority of the electrophilic aromatic substitution reaction has the first step as the redetermining step. So consider this equation in which the reaction is divided into the two steps which are actually taking place. In the first step, the electrophile attacks the aromatic system in order to generate this intermediate, which is obviously the valent intermediate or the sigma complex. It looks like this, you all know that. Sorry. And the second step is very first step, which is the decomposition of the intermediate to afford the desired compound, desired substituted compound. So in this case, the first step is the redetermining step, which is in equilibrium, and the second step is the first step, and it involves the breaking of the carbon hydrogen bond. So as the redetermining step does not involve any carbon hydrogen bond breaking, so we may expect that there will be no primary kinetic isotope effect. Sorry. But in reality, for certain reactions, we may see that the Kh by if we perform an isotope leveling experiment, then we may observe that the Kh by Kd ratio is equals to 1 to 3. That is, the Kh by Kd ratio lies between the range 1 to 3. So what is the reason for this? Okay, let's consider the two possibilities. Number one is when the rate constant for the second step, which is K2, is very greater than the rate constant of the backward reaction of step 1, that is K minus 1. So in this case, the intermediate is rapidly converting into the product. So any reversion of the intermediate into the starting material have no significance in the overall rate for this reaction, since the conversion of this intermediate into the starting material is very higher than that of its reversion into the starting material. So in this scenario we cannot observe any isotope effect if we replace the hydrogen by deuterium or tritium. However, if K2 is less than or equals to K minus 1, then interesting things may happen. So if K2 is equals to K minus 1 or less than K minus 1, then the decomposition of this intermediate into the product and the reversion of this intermediate into the starting material are almost equal. So in this case, if we replace this hydrogen atom by deuterium, then the K2 further lowers. The value of K2 is further lowered, since this step involves the carbon-hydrogen bond breaking. So now the important thing is that the reversion of the intermediate is now of much more significance than in the previous case, where the K2 was very greater than that of K minus 1. So in this case, where K2 is less or equals to K minus 1, the reversion of the intermediate into the starting material is of much more significance, and K2 may be disturbed, and the value of K2 may be lowered by certain factors such as steric factor or electronic factors. So due to such factors, if the value of K2 gets lowered, then replacing the hydrogen by deuterium will produce isotope effects, and we can see the KH by KD ratio to increase from almost 1 to a certain value which lies in between 1 to 3. So now it is clearly understood that whenever the K2 is significantly low, then we can see the isotope effect if we replace the hydrogen by deuterium or tritium. Okay, so let's recapitulate it once again. If we consider an example of electrophilic aromatic substitution reaction, in which the first step is the redetermining step, which is in equilibrium, and the second step is the first step, which involves the carbon-hydrogen bond breaking. Now there is two possibilities. Number one is when K2 is very greater than K minus 1, and number two is when K2 is less than or equals to K minus 1. So when K2 is greater than K minus 1, then much more amount of intermediate is going towards the substituted product. So in this case, the reversion of the starting of this intermediate into the starting material becomes insignificant, and it has no overall effect on the rate of the reaction. But if K2 becomes lower by certain factors such as steric or electronic factors, then we can see isotope effect if we replace this hydrogen by deuterium and tritium, since the replacement of this hydrogen by deuterium and tritium will further reduce the value of this K2, this rate constant of the second step. So now if K2 becomes less than K minus 1 or equals to K minus 1, then the reversion of the intermediate into the starting material becomes much more significant. and due to the reversion of a large amount of intermediate into the starting material, the rate of this first step becomes slower, and the overall rate of this reaction becomes also slower. So now in this case, if we replace the hydrogen by deuterium or tritium, then the value of K2 gets further lowered, and we observe a primary kinetic isotope effect in which the KH by KD ratio was found to be between 1 to 3. So let's consider this example to understand and also to predict which reactions will show the partitioning effect and which reaction not. So let's consider the diazo coupling reactions of these two naphthol derivatives. This is the 1 naphthol or alpha naphthol, this is the beta naphthol. So obviously the phenolic compound, when undergoes diazo coupling reactions, the medium should be alkaline. Classic choice of the base is sodium hydroxide. So in alkaline medium, the first step is the attack of this nucleophilic carbon into the nitrogen center to form this intermediate. Let's number the intermediate as 1 and this as 2. And the second step is obviously the removal of this proton by the base to generate the desired coupled product. So obviously this is the rate determining step, and this is the first step, and this is also the rate determining step for this reaction, and this is the first step. This is the slow step, this is the first step. So obviously this K1 and this K-1 values are different than that of this K1 prime and this K-1 prime. So we have to find out the difference between this K2 value and this K-1 value with that of the difference with this K2 prime value with this K-1 prime value. The larger the difference, the larger the difference, and the greater there will be no chance for partitioning effect. So in the first case, as we see, the first step is almost identical for these two reactions. The attack of the diazonium salt by the phenolic system, or rather the beta naphthol system, in this case alpha naphthol system, and in this case the beta naphthol system attacking the diazonium salt. And obviously the backward step also is same for these two reactions, since the decomposition of this carbon nitrogen bond is essentially same for both these two reactions, since there is no additional factors affecting this carbon nitrogen bond breaking. But in the second step, things are different. The base approaches from the opposite side of the CH bond and abstracts this hydrogen to re-aromatize the system. If we look carefully, the approach of the base is much more hindered in the intermediate 2, since there is a SO3- group which exhibits the steric or electronic repulsion towards the OH-, which is also both these two groups are negatively charged, SO3-, OH-. So there is a certain kind of hindrance in the approach of this OH minus in case of intermediate 2. Thus the K2 prime is much more lower than that of K2. So now we can see that K2 prime is much more lower than K2, but these two are almost same. So the difference, so in the second case, K2 is almost equal or less than, sorry, K2 prime is almost less than or equals K minus 1 prime. So this suggests that in case of reaction 2, we can expect there will be a partitioning effect which will produce an isotope, primary kinetic isotope effect, and the observed KH by KD ratio was found to be 5 for this reaction, and in this reaction there will be no such primary kinetic isotope effect. Okay, so that's it.